So, hello everybody, my name is Ionut Balosin, and today we are going to discuss mainly the features at the language level from JDK9. Few words about me: I'm software architect in Luxoft, and apart the software architect activity, I also conduct trainings, especially on performance and tuning. I'm quite keen on that one, and software architectures. If you want to get in touch with me, you can find me on Twitter, or why not directly on my website, ionutbalosin.com. So all of this being said, let's start by explaining what demystify means actually. As per Cambridge definition, to demystify means to make something easier to understand. However, my definition is this one: to make Java language features easier to be understood by digging inside the JVM internal. So basically during this talk, I'll try to share with you how these features are working by providing a bit of assembly code, not too many actually, and bytecode. And this is, I'm a big fan of Richard Feynman, and this is the code that really motivated me. For example, he said that explore the world, everything it's nearly interesting if you go into it deeply enough. That's why during this talk I'll try to make it easier by going deeply inside those subjects. And this is the agenda for today. So we'll cover all of these topics, all of them added in JDK9. And as I was already said, I'll try to provide you some proof how they work under the hood. Just before to start, this is a bit about my configuration in terms of hardware and software. For example, the CPU, it's important because I also have some benchmark tests, but also the operating system, everything was done under Ubuntu 16.04 and using, of course, the latest JDK9 release. And I was using Java Micro Benchmark Harness. First topic is in regards private interface methods. What is the private interface method? As the name tells, you can add, for example, private methods inside an interface. And this came as part of JEP 213, which basically contains a lot of such small features. And private interface method is just one feature related to this JEP, actually. How it looks like in practice: suppose you have an interface, and inside that interface you have a default method foo, which was added since JDK9, and for example you can dispatch the call to a print method, which basically is a private interface method. Why such need to add private interface method? It's very trivial, the answer, because to better structurize the default methods, to avoid having default methods too heavy in terms of a number of lines. How it works under the hood, for example, if you compile it and decompile at the bytecode level, as for the ones not quite familiar with the bytecode, I won't insist too much. I will just figure it out that under the hood, the print call, as you can see here, is tackled using an invoke special. Invoke special, it's the opcode at the bytecode level, also used for all other private class methods, which concludes basically that these private interface methods, for them, there is nothing in particular to tackle them at the bytecode level. The mechanism is the same as we have, for example, for such private methods in whatever class. More than that, the default keyword, because you see here, for that default method, the default keyword after we compile and decompile, at the bytecode level, there is no default keyword. So default, it's just at the very high level language. It doesn't exist at the bytecode level. This was first category. The next category of such private methods are private static interface methods, and they are handled in the same way. Suppose you have a static method, which is buzz, and that buzz calls a static print, which does a system.out. How it is tackled at the bytecode level, if we desugar that call, there is an invoke static, as you can see there. Invoke static, it's also the opcode used to call any other static class. So it's not something particular for the private static interface method. So to conclude, up to now, we saw that in order to tackle these private interface methods, either static, either non-static, the Oracle guys, the JDK guys, relied on the same mechanisms. They didn't add something in particular. But this is very simple, right? I would like to share with you a more interesting example. When I see here more interesting, it's also a bit more complicated. Let's see how it looks like. Suppose we have a functional interface which contains the method run. So we just define a method and we bound that method inside the functional interface. And we declare a class called main. And inside that class, we have an inner interface, a private interface, a nested interface, which declares this private void print, which is actually a private interface method, which does very simple. It just prints out this message. In the main method, what we have here, we have a functional interface. And for that functional interface, we assign an instance of this anonymous class by using the resolution operator and using a reference to this private interface method. To conclude, this single line, it's basically contains an anonymous class casted to a functional interface by using a private method reference. So this is our main statement, and let's see how it works under the hood, because it also contains a private interface method, which is referred as a method reference. So first of all, let's focus on this new inner. Every time when you create such instances of anonymous classes, right, what happens, the JavaC generates that main $1, main because the main is the outer context, the enclosing scope, and $1, this is the default naming scheme. So JavaC generates this class for you, which if you want to zoom inside it, what it has, it just implements the inner, because it should implement the inner, right? Because the inner is our interface, and automatically it contains the default constructor. However, at the bytecode level, because there is a new something, this new something corresponds to these three instructions at the bytecode level: new, dup, and invoke special. Every time you create an instance of something, there is a new, a dup, and invoke special. These are the three opcodes specific for creating an instance. So what we have until now, we saw that this new inner creates under the hood a class, which is this main $1, which implements the interface. But then if we focus on the print method, we see there is a private method reference to the print method. How it looks like, the bytecode generated, it's desugared into an invoke dynamic. Invoke dynamic was added since JDK 7. However, it is extensively used in JDK 8, for example, for lambdas. And in this particular case, for method references, they are tackled in the same way using the invoke dynamic. And if we see this invoke dynamic, it's a bit complicated. I won't get too much into these details because it's out of scope. What is a matter of interest in is, if you look at it, you will see, for example, this main dot lambda $main $0. However, you saw the initial implementation for the main class. There was no lambda $main $0 method. However, this is so-called synthetic method generated by the JavaC. And how it looks like, it's a synthetic method that does only the call, dispatches the call to another method, which at this stage might seem a bit weird. It's called access $000, which actually dispatches the call to the print, and it will be clear in a few slides. So basically, what it's important at this stage that Java-C generates this synthetic method, which basically desugars the Lambda body. And another thing regarding to this invoke dynamic is that when you hit the call side, when you actually trigger the invoke dynamic, what it generates an instance of a VM anonymous class, which is called main $lambda $49. Basically, all the times you use lambdas in your code, the VM generates such classes, $lambda counter. And how they look like, let's see what's the structure. If you want, for example, to dump all the generated Lambda classes in your application, you can use this internal Lambda dump proxy class, and you specify a specific path, and under that path, all the VM anonymous classes will be dumped. And how such class looks like, it's very simple in essence. It implements the functional interface, it has a constructor, and it has a get lambda which returns an instance of that. And this, you may wonder, for example, what is that 49? 49 is basically a counter, because all of these classes are generated using a Lambda meta factory, basically based on a factory, and every time you the VM itself generates a new such class, it encounters the counter. So basically 49 means that this class was the 49th class generated since the JVM has started. And at the end, what we have, actually, because the functional interface, iFunctional interface, has the method run, of course, the generated class should implement this method run, which basically contains just a dispatch call back to the main. So if we get back to our initial example, and now let's suppose we call the test.run. So we saw how the new inner, what it generates, how print method reference is desugared. But now let's see how it works when we say test.run. When the test.run is called, what happens? We saw that the call is dispatched towards this main $lambda $49, which I was saying it's basically a class which JVM generates on the spot, and by default it is not dumped on the file system. You can dump it explicitly by using that flag. And this is just calls the run method, which what it contains, it's a very simple method. We already saw the run method that contains actually dispatch back to the main method inside the lambda $main $0. And what it does, this lambda $main $0, is a synthetic method we discussed about, and it contains a call to the access $00, which is basically access $00. It's a method which belongs to the myInner interface, and why it was added there, recall, print was a private interface method, and those private interface methods cannot be called from an external class. However, we need to do that, so that's why Java-C adds this let's say mechanism, or leverage on this mechanism, by generating this access method, which in essence calls the print. So it calls the print and returns back the result. So as you can see, this example using this anonymous class, the resolution type for the private interface method generates a lot of classes under the hood, and it's a bit complicated. Roughly speaking, or in a nutshell, I would say there were a few generated classes with synthetic methods generated just to handle that call. And another case, another scenario, very coupled with the one which I was already described is this one. For example, let's suppose we keep the code as it is, but we remove the explicit cast, because in the previous example we explicitly casted the instance of that anonymous class generated to the inner, to our interface. If we remove that explicit cast, what do you think it might happen? The question is, will this code compile without the explicit cast, or it won't compile? And of course, I won't answer. You may think yes or no, but let's see in reality what happens. So we have an error. We have an error because if we remove that explicit cast, recall when you say here new inner, it creates that main $1, and main $1 doesn't have any print method in it. The print method, it's a private method which belongs to the interface. However, this is rejected by the Java-C, so the compiler is right in rejecting that. However, the diagnosis is wrong. So there is a specific task raised on the JDK side to say that it shouldn't be like that. So for example, it should be equivalent to the first one even if we remove the explicit cast. So hopefully it will be fixed in 11. So this is a limitation with this functional case. The next scenario is about strings in Java 9. However, if you have questions, I would advise you to ask me at the end, just to have the presentation to make it more smooth. And at the end, we will have time for questions. So please write them all and I'll answer everything at the end. So strings in Java 9, what were the changes added to the string 9 to the string in JDK 9? If you probably know, the string until JDK 8, including JDK 8, was backed by a char array, and there was an int for the hash and all these kind of things. However, in practice, due to the fact that a lot of strings could fit Latin 1, for example, the Latin alphabet, these could be stored by 1 byte. And storing them on 1 byte instead of 1 char, for example, as it was before, we minimize this. We actually minimize a lot the footprint for all the strings created during the runtime. So they created this scheme, which is called compress strings, which is implicitly added, which, for example, decides if a string could be compressed. I mean, all the characters could fit in 1 byte. The Latin 1 scheme is used. However, if it is not the case, it switches back and stores everything. It's encoded in using UTF-16. And there is a byte for the flag, 0 and 1, saying that Latin 1 or UTF-16. So this is a real representation of what I was saying. For example, you have this new string allocation, which is called Java-C, and you have UTF-16. As you can see in UTF-16, for each letter there are 2 bytes. However, one of those 2 bytes, it's useless because it's always 0. If you want to compress that in Latin 1, there is only 1 byte, so implicitly the size, the footprint on the heap, it's reduced. If you need to measure this, for example, I did it with Eclipse Memory Analyzer, and in cases with UTF-16, as you can see, the retained heap is 56 bytes, and in case of Latin 1, the retained heap is 48. The retained heap means, for example, the total number of bytes that might be deallocated if I get rid of that string. And of course, the difference will be bigger and bigger with the number of strings that are encoded using UTF-16 versus Latin 1. In comparison with a string that has UTF-16 specific character, which is this Java-C, the last C has that accent, and in this case, the string couldn't fit in Latin 1 encoding scheme because it has at least 1 character that doesn't fit. So in this case, it inflates and it is stored on UTF-16, which implicitly says that for each character out of the initial string, it is backed by 2 bytes inside that byte array. And this comes with a cost because, as you probably might think of, UTF-16 string sizes actually adds this constraint. If you declare, this is a piece of the code out of the JDK sources, so if you allocate a string which is backed by UTF-16 encoding, because for each character from that string you need 2 actually bytes in that byte array, you half the size of that string, and you actually can't allocate, for example, a string which has the length more than half of the integer max value. Why half of the integer max value? Because implicitly all the arrays, you can allocate one array of maximum integer max value, and being half of it, of course, for UTF-16 you need to half the size. This it's not valid in case where you have strings for using Latin-1 encoding, or it wasn't the case previously in JDK, for example, 8, where everything was backed by 1 char. Now, a few things about how it works, for example, when you construct a string. When you construct a string, what happens? First, by default, if you are using compact strings scheme, which is enabled, I was saying that it's enabled by default. If you are using this one, the string implicitly tries to compress to Latin-1. If it fails, if the compression fails, meaning that there is at least one character that couldn't be, needs to be stored on UTF-16, it switches and it is stored using the UTF-16 encoding. So by default, it tries to compress in Latin-1. If the compression fails, it switches and stores in UTF-16. And I did the following test. Suppose you have an application where the majority, or probably almost all your strings are UTF-16 strings. And I did this benchmark method where I concatenated all of these strings, right? And I measured the time for the default option with compact strings and without default option. Compact strings, I was saying, is the default one. And if you want to disable it, you have to specify the JVM flag minus compact strings. And what I figured it out is that in case of compact strings, the number of nanoseconds per operation was less, which means in this case, it was better from the performance standpoint to disable the default compact string feature. Because why is that? Because if the majority of your strings could fit in UTF-16, there is no make sense to try to compress them. The compression would certainly fail, and you will switch bail back in UTF-16. So you can benefit of that time. However, the number of bytes allocated per operation, it's roughly the same. So the conclusion is that if your application intensively uses UTF-16 characters, maybe I recommend you to keep this in mind. You might increase the speed by disabling this compact string feature, which is by default. The second part, another story is what happens, because we know at this stage that everything is backed by 1 byte or 2 bytes. But what happens if you, for example, have call string.char or string.toChar array? You need, of course, to retrieve a char or char arrays out of that byte or byte array. This scenario is called inflation, when you, for example, have a byte and you need to get out of it the char. And here is the sources out of the JDK, how it works. It's very simple, actually. For Latin-1, the char at method, what it does, it gets the byte, and there is a logical AND between this and FF. However, in case of UTF-16, there are 2 bytes that could be merged using this and bitwise operation, and at the end it returns the char. So it's quite trivial. However, I tried to measure the performance that I was spent, because the Oracle guy says that we don't want to regress the charret or to char array, right? So I took these two strings, one in Latin 1, the second in UTF-16. Why is that UTF-16? Because at the end it contains few UTF-16 characters, and I measured the time to for the two char array in both cases, and the time to say to retrieve a char based on that specific index. The timings that I retrieved, and here I included also the comparison between JDK 8, update 172, and the current JDK that I'm talking about, JDK 9. And as you can see, in case of Latin 1, and UTF-16, the char at, the performance, it's almost the same between those two. And also for Latin 1 and UTF-16, for two char arrays, the performance, it's not very different. It's marginal, I would say, which leads me to the conclusion that inflating from one byte to one char, or from a byte array to a char array, has minimal performance impact from JDK 8 to JDK 9. The next one is about string equals, because we know at this stage the string is backed by a byte array and a coder which says if it is Latin 1 or UTF-16. Imagine if you compare two strings that have different coders, the comparison is extremely cheap. Thing that didn't happen before, where we didn't have the encoding scheme. Because, for example, it doesn't make sense to go and to compare them if the coder is different. And what I did, I took 4 strings, two groups of identical ones, like Latin 1, UTF-16, UTF-16, and I did 3 kind of benchmarks. Latin 1 compared to the same Latin 1, UTF-16 compared to the same UTF-16, and Latin 1 compared to UTF-16. And the timings that I get, here are the timings. With the default JDK, what we have, in case of strings having the same coder, like Latin 1 or UTF-16, the performance, it's almost there. For example, 5.9 versus 6.4. Here it's slightly better, because the Latin 1 has less bytes in that byte array to compare. However, the most noticeable result is this one, Latin 1 to UTF-16, which proves, actually, if you compare two strings backed by different encoding schemes, the performance it's quite good. It's very low. And also if you disable the compact strings, which means everything it's backed by 2 bytes in that byte array, you can see the performance, it's almost the same in all cases. However, the last scenario is, you may probably know, for example, including JDK 8, when you concatenate two strings, it was backed by the string builder, append, and so on. However, in JDK 9, there is not the same. In JDK 9, they switched and they are backed by invoke dynamic, which uses under the hood a string concatenation factory to concat all those strings. So actually, they removed this string builder that was generated by the JavaC, and they concatenate during the runtime inside that concat string factory, which gives you opportunity for the feature, if they upgrade or if they enhance or make them more performant, the concatenation mechanism, just by upgrading from one JDK to another, you benefit out of those features without recompiling the bytecode actually. But here it's a very tricky scenario. Let's suppose you have this concat class, which has a inner class which is called message, and the message contains an array of strings, and I override it, the method toString, and on each call, it returns actually a string out of that array by, of course, incrementing the index. And here inside the main, what I have, inside the main, I create an instance and I say system.out, very simple. However, if you compile this with JDK8, it prints what you might expect to. It prints Java conference, right? Because it calls message.string and message.string. If you compile it with JDK9, it prints in reverse order. It prints conference and Java, which seems a bit weird, right? Because we didn't expect. What is the reason? I was telling you about that string concat factory and the invoke dynamic. The thing is that if you can fix this, if you change the default string concatenation strategy that it's used during the runtime, and you, for example, use one of these bytecode generation string builder. However, you can also use, for example, bc_sb, bc_sb size, bc_sb size exact. So all of these strategies relies on the bytecode generator scheme and string builder. It's similar to what we had initially at the bytecode level. The next category, which is by the default, the next strategy, which is by default, it's based on a method handle, and it's called method handle inline sized exact. It uses actually directly a byte array, which implicitly it's more performant, but it has a regression. And not only this method handle strategy has a regression, but all the MH strategies present in JDK 9. And this is also a JDK task raised. It will be fixed to keep this consistency. It will be fixed in JDK 11. After JDK 11, if you have such corner cases, I would advise you to switch the default concat strategy for the string concat factory, because it fails in the sense that it invokes toString method in reverse order. StackWalker it's the new API added in JDK 9. What it says actually, it's a very easy way, for example, to inspect the stack frames in its laziness. It's like we have for the streams. You can also specify the max number of stack frames, the depth for such iteration. And also you can filter all of those frames. Plus, on top of that, implicitly it is more performant because the previous API, like for example, get stacktrace, it needs to fill the entire stack with all the frames. Now it's not anymore the case, because you can specify the depth and you can, for example, filter the frames. So the API is very simple. StackWalker get.instance. You can specify few options. For example, if you are interested in getting the color frames, if you want to get the reflection frames, if you want to get, for example, some hidden frames. Remember the synthetic methods. By default, those synthetic frames belonging to synthetic methods are not printable inside the stack trace. So if you want to do that, you need to explicitly show hidden frames. And also you can specify the maximum depth, how many frames to inspect, and not more. I did two scenarios. I created a recursive method until I reach a certain depth. And once I reach that certain depth, I traverse backwards the frames and I measure the time. And this is the code using StackWalker API. So this is the method, the benchmark method. So the benchmark method calls another recursive method. The recursive method, it's calling itself until the depth is reached, because the depth is actually decremented, sorry. And at the end, once we reach depth 0, we iterate to the frames. We skip n, the first n-1, and we get the end frame. In comparison with the classic API getStackTrace, the classic API, what it looks like, it says thread current thread dot getStackTrace. So in the same way, you create a stream out of it, you skip the first n-1 and take the end one. In terms of comparison, the comparison, as you can see, in case of StackWalker API, in all the cases, it was better, especially the difference, it's if the number of frames are quite few, for example, 110, there is a big discrepancy between this one and getStackTrace. However, if you increase the number of frames which are inspected by both StackWalker and getStackTrace, probably there be somehow closer, but for few frames, StackWalker API proves better. And the second test case that I did, I just incremented again the number of frames by doing that recursive call. I stopped when I reach a certain level, and I try to measure the time in getting the current stack frame. How it looks like, the code is similar to what we had before, the same recursive method, but this time I walk only the first frame and I return it. In comparison with the classical approach, where I get the entire stack traces, the array of, and I generate a stream out of it, and I say, give me the first one. And here, as you can see, very, very big discrepancy in performance between StackWalker API and getStackTraces. And as you can see, on top of that, the getStackTrace API, it's proportional actually with the stack depth. So bigger the stack depth is, more time it takes for you actually to fill in the stack trace and to create the stack element array, which is not the case for StackWalker API, which is laziness, and it's based on a specific depth. But even this is not the best way. If you can afford in your applications to process the throwable frames asynchronously, and if you compare to the synchronously StackWalker API, why it's synchronous? Because the StackWalker API, it's called in the caller thread, so it is synchronous to the caller thread. How it looks like, this asynchronous. So let's suppose you have a throwable, you create a new instance, you get the instance and forward the instance to another thread, and you process that in an asynchronous way. And if you compare this approach of processing asynchronously the throwable frames versus StackWalker API, you will see that the new throwable, here I measured only the cost of new throwable, it's very cheap, which leads me to the conclusion that if your application or your business context is suitable for such scenario, you can even don't rely on StackWalker API, so you should use new throwable, get the exception, and then in the asynchronous thread process all the frames. So you'll benefit even more of more performance during the runtime. The next API was in regards to the collections, how it looks like, for example, and more specific to create unmodified collection instances. For example, until JDK 9, there wasn't such very compact API to create unmodifiable lists, sets, and map. Now they added this API. How it looks like? Let's start with the list.off. List.off, for example, if you can see, list.off contains a lot of methods for first 10 elements, which might seem redundant methods because you can see for 3, 4, 5 parameters, there are dedicated methods. However, starting with the 11th parameter or 11th argument, more precisely, there is a vararg implementation. And if you would see such code in your application, you probably would ask, why is this implementation? The question, it's obvious. The answer, probably not, because what happens here, it's a bit of assembly code. I know we are Java programmers, we really don't care about assembly. However, trying to understand things in a proper way, you need to have a basis about assembly if you want to understand the full depth. What happens when you call a method which receives varargs parameter? Basically, before that method being called, the last line, all of those parameters are retrieved from the stack. If you can see, get field parameter 1, 2, 3, 4. There is an array which is allocated. All of these parameters are mapped inside, are referred to that array. And then the method containing varargs parameter is called. So this is why, for example, you pay an extra cost if you have varargs methods versus methods with a specific number of parameters. And here I did a test just to prove that. I created different methods having explicit number of parameters versus number of variable arguments. As you can see here, the blue figures are the better in all the cases invoking a method having explicit parameters versus invoking a method having a variable number of them, or varargs. It's always better. So that's why the Oracle guys, being smart guys, of course, they decided to add this trick in the JDK library. And if we have to zoom in even further inside the off methods, for example, we have off E1 of 1 parameter, 2 parameters, 3 parameters, we can see specific wrappers, which is list 0, list 1, list 2, list n. Roughly speaking, we have custom wrappers from 0, 1, 2 elements, like 0, 1, 2 here. And starting with the third number of elements, there is this list n. And how this list wrappers looks like. For example, in case of list 0, it contains only 1 element. In case of list 2, it contains list E0 and in1. And in case of n, it contains this array. And still, again, you might ask yourself, why such implementation? And with basic understanding about the memory and about the CPU, the answer may seem quite clear. So if you have, for example, an array, and that array has references to another objects, like is this the case, you pay the cost of indirection. First of all, the elements might not be allocated actually. And for example, calling one element, you have, using the array approach, you have one more level of indirection, plus calling the second element out of the array, there are better chances to fall inside a cache miss, because as opposite to the second case where the elements are one to next each other declared and not using the array, they are compacted. So calling E0, for example, there are bigger chances, if it is less than 64 bytes, for example, to retrieve automatically the next E1 on the same cache line. So you basically minimize the number of CPU cache misses. So that's why we still in Java needs the project Valhalla. We need value types for better packaging the values. And if we have to measure as well the footprint, let's suppose using the previous API, JDK8 and JDK9. In JDK8, you need to explicitly declare an array, and you call collections.onModifiable list, versus JDK9, which is very compact. In case of JDK8, you can see really a lot of number of indirections, because that collections unmodifiable list, it's backed by this unmodifiable random access list, which has a reference to the array list, which contains an array of objects and has each object in itself. In total, the retained heap, it's 80 plus 24, it's around 104 bytes. In comparison with the JDK9 version, with two strings, it's very compact. It's that particular or custom list2 wrapper, and it has actually E0 and E1, and the total number of retained heap in terms of bytes is 24. So also it's more compact. In terms of performance, if you compare the same list of versus the classical API, by creating such list using different number of elements, 1, 2, 3, 10, 11, and so on, you can see it's always quickest. Just to sum up what we have discussed, list of brings less overall space, improved reference locality, and faster creation time. And if we zoom inside the set of, you will see it's exactly the same idea. Fix methods for less than 10 elements and the var args. In terms of wrappers, it's the same, set 0, 1, 2, and set n. So I won't repeat anymore what I have explained. And in terms of performance, as we can notice, the .off method, which actually creates such list of 1, 2, 3, 10, 11 elements, was always better in comparison with the classical unmodifiable set API. The same happens in case of map.off. For example, you have specific methods for less than 10 key value pairs. Starting with the third one, you should rely on off entries method, which is basically a var arg method. The same for the wrappers. There is map1 and map2 as wrappers, and mapn for more than one pair key value. In terms of performance, what I did in here, I compared, for example, the creation time using the off method for different number of elements, the classical API unmodifiable set, and here I foolishly used, for example, the off entries even for less than 11 key value pairs. The thing is that off entries was always or almost always proved as being the slowest. However, what I've noticed that in few cases, the performance between map off and unmodifiable map was somewhere the same. For example, in case of 2, 3, 4, 10 elements, which still concludes that off it's good, but it's not much difference in performance between off and unmodifiable set. However, if you think about the footprint of the memory, of course, it is more wasted in case of unmodifiable map. The next one, it's about onSpinWait, which is quite interesting. onSpinWait was a new method added in JDK9, which belongs to the thread class. So if you zoom inside the thread class, you will see this onSpinWait. What it basically does, it tells the CPU there is a busy waiting spin loop, waiting for something to happen, but that event could happen very frequently and it finish very quickly. So this onSpinWait, it's a new method which is suitable for such situation where you have, for example, shared memory variable, you inspect it and you listen for events that might happen very frequently, but they finish also very quickly. The advantage of using this onSpinWait is that you don't actually release the CPU, you actually delay the execution of those instructions on the CPU. And we will see how it is implemented on x86 architectures. So basically the API, it's like this. While I'm waiting for a condition which is not satisfied, I could say thread.onSpinWait. This is a possible scenario that you might use. For example, you have a producer and a consumer, and suppose that producer produces a lot of items, and if it is not ready to produce, it spins away a bit, and then it produces the item and continues until it signals the finish to the consumer. The consumer, what it does, if the finish is not signaled, it asks itself, am I ready to produce? Yes, of course. Thread.onSpinWait and then consume. However, if you compare this approach, because you might see, of course, why I shouldn't use yield, for example, why I shouldn't use sleep for 1 second, why I shouldn't use wait notify, and all the other possible situations. I was saying this onSpinWait is suitable for events that happen very frequently and for very short period of time. onSpinWait, as you can see here, took me, for example, 47 microseconds per operation, was very fast in comparison to yield and sleep variants. However, the number of context switches is also important, because you profile the number of CPU context switches. You can find that in terms of onSpinWait, there were less context switches. For example, in case of sleep, there is also a context switch, because the thread is descheduled and another thread may acquire the CPU. In case of yield, there might be a context switch, there might not be a context switch. You are at the mercy of the OS scheduler. But for the onSpinWait, there is no context switch, because what it does in onSpinWait, it's backed by pause assembly instruction. Pause, it's very old instruction. It is there from Pentium 4, and what it does, it basically delays a bit the execution for a finite period of time, preventing the pipeline to be filled by instructions, and implicitly it reduces the power consumption, but it doesn't release the CPU. And that's why I was saying it's suitable for that context-specific scenarios and offers more performance in regards with the others. And here, be careful, because using this one might not work for Spark, because on Spark there is still an investigation what intrinsic is suitable for such architecture, but on x86 architecture it seems good. And the last one, it's about contention locks in JDK9. Actually, it's not quite a language feature. However, if you have contention, what means contention? You have multiple threads trying to access or acquire the same lock, right? There is a contention situation. And in this case, where you have such contented scenario, the JDK, starting with the 9th one, was dramatically improved in case of these areas like enter, exit operation, notify, all, or unpark. And here is what happens, for example, if you have multiple threads trying to access the same lock. If the thread that can't acquire the lock, at that stage, it goes inside the wait queue, and once the thread that owns the lock releases it, it notifies the thread from the queue, and the thread from the queue tries to acquire it. And this happens actually when you have this contention, the heavyweight locking scheme, it's also called, on the same lock instance. And I did a test. What I created a synchronized method, and inside that method I simulated a bit of intensive processing. Why intensive? Because I was using a volatile, and each thread actually needs to do this computation, and I shared the same method across multiple threads. And the tests, the figures are as follows. Here, using bias locking scheme and heavy monitors, without heavy monitors, is the default JDK figures. And as you can see, the default JVM options are suitable. In case of contention, it's somehow, at least on my hardware, at least less than 32 threads. However, if you increase the number of threads, the default JDK scheme didn't prove as being suitable, and in this case you should rely by disabling the bias locking and explicitly enabling the heavy monitors of this contented locking scheme that was improved and was added in JDK 9. So take care this scenario. If you have a lot of threads or sharing the same lock, it's probably better to consider enabling the heavy monitors. However, if the contention is less, as it was in my case, up to 32 threads, probably you should let the default JDK parameters. And all of this being said, I'm closing the presentation. If you want to get in touch with more resources, there is a presentation from Alexei Shipile for compact strings, Monica Beckwith from contention, few words about collections from Stuart Marks. Brian Gyotz has a very nice article about Lambda translations, and also Andrei Pangrin, very smart guy, also about stack traces. So here are a few bibliography if you are interested in more. So that's all, guys. Thanks a lot. And now I'm ready to answer your questions, actually. That's why I was saying, just to be smoother, I would prefer to have them at the end. So please post all of the questions in this channel. So I'll start to read. The first one from Christoph: is this measurement of stack trace not mess up by using streams? They have their own costs. Yes, indeed, but indeed, it could be, but it's negligible. I mean, in such case, it's comparable the streams impact in both cases, because in both cases the streams were included in the measurement. But yes, if I want to refine this, I would isolate the thread get stack trace, and then I will dispatch to another, and I measure the time, and I'll print that out. So yes, you are somehow right, but nevertheless, it's still an idea. And the next one from Christoph, of the measurements was doing, yes, GMH, I was telling in the first slide. What is the practical purpose of interface private method? So I was already told you that. So private interface method were added, for example, if you have a long interface methods and you want to split those methods in other methods, and you just call them, just for readability of the code. What is the overall purpose of the private method interface? Methods is the same. So actually, just to better structurize the code, because with default methods from JDK8, the people might create heavy default methods, very huge methods. So with private interface method, you can refactor and use those private. It's the same approach as a normal method and normal private methods. Can you send a mail to all listeners with the presentation? No, I can't. The presentation is also recorded. It will be published on the Luxoft website. So you can find that presentation online, actually. Thank you very much. Very interesting. Yes, so there will be a recording link. So the organizers will publish the presentation. There is no problem with that. A link to the presentation, please. I mean, if you refer to the slides, it's not possible. And to be frank with you, I'll go to a lot of conferences this year with this presentation. So that's why I prevent publishing in advance the presentation. This is the reason, but it doesn't care actually for you, because you have the recordings on the Luxoft website. So I don't see any problem with that. Okay, any other questions? So what is the reason of accessing private interface methods outside of interface? I don't think it's possible. Outside of an interface, what I was telling, because it's private, right? What I was showing you initially was actually a corner case where you are inside the same class and you use reference method, which is a private interface method. So that was a corner case actually. It was a very, very tricky corner case, but other than that, in normal production code, you shouldn't complicate the things in such way, actually. Can you share only library links? Library links, if you refer to library links, I don't understand, but I was using the GMH, Java Micro Benchmark Harness. I didn't use any other library link. So the Java Micro Benchmark Harness is this one, actually. So it's included in the JDK distribution. So there's nothing to share with you actually. And if you Google Java Micro Benchmark Harness, you will find it on Google. So I didn't use any specific library actually. I don't find it on Lux of Confluence. If you mean the recording, if you don't find it on Lux of Confluence, it will be published in a week or something, I guess. So there is a shared workspace with all the recordings from also previous session. So it will be there definitely. Did you compare array as list with list of? No. What's the case of that? I was comparing not arrays as list with list of actually. I was comparing list of with collections dot unmodifiable list. And previous, to be able to use collections dot unmodifiable list, I created an explicit array list, but I didn't compare arrays dot as list. Sorry, I mean links from the last one slides. Okay, so sorry, I mean links from, okay, so probably the biography you are interested in. 1 second, I mean this one, I think you're referring to. You can do a print screen actually. Yes, you can do a print screen on this. And if you just Google by the naming, you will find all of them. Okay. What else? Yes, answer live. Okay. Live. So getting back to Robert Moldovan, what's about list of and versus a release? I don't know to answer because I didn't do any comparison. So you are free to do it. It's quite straightforward, but it wasn't included in the presentation actually. So I have no answer for you to this question. Okay, good. Anything else? It was quite good audience, 150 attendees. If you have any other questions, guys, or you can tweet me. I mean, my contacts on Twitter are always better for me, even better from Lux of Mail actually. So you can contact me there, or you can drop me a mail on my website. That's good on that. So if you don't have questions more, I have nothing left. So thank you for the attendance and have a lovely day actually. Thanks so much. And as I said, the recording will definitely be published on the Lux of the conference. If you don't know exactly the link, please send a mail to the organizers. They must let you know exactly where to find the recording.
Thank you, Ionut. Sure, the publishing recording in the Lux library and send notification all participants after recording will be publishing notification by mail. And I put link to all other materials from the technology community. You can find all materials on and all videos on this page. Colleagues, if we haven't got any other questions, we can finish this meeting.
Okay, I don't see any other questions. Only thanks a lot. So
Thanks again, Ionut, and thanks again, guys, for your participating.